In this video, we'll be looking at section 3 on the center of mass from the 2016 exam. Here we're asked to consider a region between the x-axis, so this line here, and the function y equals x cubed on the interval 0 to 2 for x. And that's perfect, that's what we have. So if we imagine the x cubed curve where we're going to sketch it, we would have the classic shape like this. Now we do have to indicate the vertical scale, so we might want to be a bit more precise. In particular, what we know is at 2 we're going to hit some point, and 2 cubed is 8, so we can fill in the blanks here. And the other point that we would know is 1, 1, because 1 cubed is 1, so we'd have something that looks like this. There we go. So that would be our function. And we're asked to do that between that graph, the x-axis, on this interval. So the region would be this region here. Part B, imagine that this region is cut out of sheet metal. So we have a piece of metal with this shape, it has a constant density, and we're asked to find the total mass of the region. Fair enough. The challenge here is that we need to cut this region up to find its area, and then we can take the area, multiply it by the density, which is per unit area, and get grams. So an important thing in general problem solving like this, our goal is to find a mass, and to get the mass we're going to need the total area times the density. That'll work out unit-wise. The easiest way to find the total area is simply to slice it into vertical slices. Each slice would be delta x wide, and then the height would be given by the y function, which is y equals x cubed. So the total area of a slice, we'll do this in components because it'll make looking at part C a bit easier. Total area of a slice is going to be a height times a width. And we're talking about one of these rectangles. And so that'll be y, which is x cubed, times delta x. Now if we want the total area, in fact, total doesn't really apply to this, just the area of one slice. The total area is going to be the integral, or adding all those values up, taking the dx in terms of, or writing our delta x as a dx instead. And then we integrate from x equals, where's our first slice, at 0. Then we slice out to x equals 2. All right, then we integrate that. This is all fully defined. Add 1 to the power, divide by the new power between 2 and 0. That's going to give us 1/4 of 2 to the 4 minus 0 to the 4. That's 1/4 of 16, and that is 4 square centimeters, or centimeters squared. So the total mass is going to equal 4 centimeters squared times 12 grams per centimeter squared, and that will be 48 grams. Finally, in part C, we're asked to find the y-coordinate of the center of mass. Now that makes it a little more challenging. We have our function, y equals x cubed, but to find the center of mass in y, what we have to do is imagine taking y points and multiplying by the mass at that same y point. Well, if I want points all of the same y coordinate, I have to take horizontal strips that are delta y thick. And so our y center of mass is equal to, it's not a vector, it's just a bar. That y center is going to equal the integral of y times the mass at that y. And it is going to go from y equals 0 all the way to the last slice, which is not at 2, but in the y direction, it's going to be at y equals 8 from our sketch earlier. Up here, there we go. Our final slice is up there, if we are cutting as horizontal slices. And then we take that and divide it by the total mass, which we already found in part B. So let's do the same analysis we did before. We're going to focus on this integral and just look at it. We know we can divide through later. The y times the mass of y the mass of this slice is going to equal the width times the height times the density. That product is going to give us the mass at height y. And we're going to get a dy in here for free. One of the things people love to do is just put extra d's in here. There's a real source for those d's. It comes from this delta y. Let's add the other ingredients here. 0 to 8. It looks like 0 to infinity, so 0 to 8. And we have y times the width. All right, the width is going to be the tricky part. Let's save it for last. The height is easy, delta y. And the density is easy. We already have that as 12. And we may as well, seeing as we're already in the integral form, write that as dy rather than delta y. But it's the little thickness of that rectangle. Now, the key thing for our width is this part here. This whole dimension in this direction is going to be 2. So we have the width is being taken away from 2, and how much is being taken away? It's this part here, which is the x-coordinate on our graph, which is the cube root of y. If I want to know how far this is at a certain y point, I would take the cube root of y, and that would give me the x-coordinate. And that's this distance, but I want the other half, so it'll be 2 minus the x value, which is 2 minus the cube root of y. Rewriting it one more time, and bringing out some stuff that we can bring out. The 12 is fine. We have y times 2 minus y to the 1/3 dy. That is everything there accounted for. I think we're ready to integrate. Not quite yet. We should multiply this out to make it a little easier to evaluate. We have 2 y's. Y to the 1 times y to the 1/3 is y to the 4/3. And we keep going. Now we can actually evaluate the integral. We have 2y, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Between 8 and 0, go up here, and we have a bit more room actually. We'll save that for later then. And that gives us 12 times. The 2's cancel. We don't need those anymore. We have y squared, which would be 64, minus 3/7 of 8 to the 7/3. We'll have to take a look at our calculator for that. And minus 0, so that's nice. So what do we get from that? Well, this will take some calculator work. Let's do that on the side, and we'll see what we get. That gives us 12 times 64/7, or if you like decimals better, 12 times 9.14 and some other stuff. 9.1429, let's say. Well, that's almost what we need, except we also have to factor in the total mass from part B. So then going back to our original question, what's the y center of mass? It's going to be 12 times 64/7. We'll keep it nice. Oh, divided by 48. That was our total mass. And so we're using this equation. That gives us 1/4 of 64/7. And that is 16/7. And 16/7, if we want a decimal value, is around 2.29. And we can check whether that makes any sense whatsoever. The y center of mass should be a point between 0 and 8. Yes, it is. 2.28 would be around here. And it doesn't seem unreasonable that if we balanced this sheet of metal on that point, that we would have a balance between the forces. We have more area here, but it's closer to the axis. On this end, we have less area, less weight, but some of it is further out, so it carries more moment if you're into that kind of thing in physics. For us, it's enough to know that it looks like it's relatively balanced. And so we end up with 2.29 as the center of mass.